Welcome. This is an update on the tree forest ratio. I talked about this before, but I didn't say anything about the proof. I want to say something about the proof today. First of all, the setup. We have a finite simple graph, arbitrary finite simple graph, and then we can look at the number of rooted forests and the number of rooted trees, and we can look at the ratio of this. And that's the tree forest ratio, and I was interested in the case when we take barycentric refinements of the graph. What you take is there's a new vertices each time you take the complete subgraphs and you connect to if one is contained in the other. Purely combinatorial, nothing Euclidean involved at all. And what we also have is here in that definition is the pseudo-determinant because of the forest theorem of Chebotarev-Shamis and of the tree theorem, matrix tree theorem of Cayley. What I want to prove today, it was mentioned that if you take the logarithm of this tree forest ratio and you divide by the number of vertices, you get a constant which only depends on the dimension, the maximal dimension of the graph. So maximal dimension is just a maximal complete subgraph, maximal clique which you have. For example, and that's a case which we completely understand, everything is completely known, is in dimension 1. If there's no triangle in the graph, then when you are doing refinements, you get only the forest growth really matters, because the trees grow polynomially n squared and the forests grow, essentially for Fibonacci type with the Lucas type number, and you have the number is 2 times logarithm of phi, explicitly known. Golden ratio appears here, and so it's interesting that in the one-dimensional case you have exponential growth of the forest, but polynomial growth of the trees. But that changes in two dimensions and higher dimensions, and then you see just in things change pretty drastically. Also with the equilibrium, what we are talking about next, about equilibrium measure, and everything changes. It's no more smooth in higher dimensions. I want to prove this with just building on the Barycentral limit theorem. I call this now Barycentral limit theorem, like the central limit theorem, which is a theorem in probability theory. And actually probably this is easier to prove than this. I proved this in 2015, wrote 2 papers about it. I never submitted any of the papers. It's kind of obvious once you see how it works. It uses a theorem of Litsky to estimate the estimates, and it's pretty clear once you understand the growth of the f vectors and everything. So you can do everything explicitly. I'm actually happy that I didn't kind of bother with referees, etc. in 2015, because later on I got some interesting new results on connection calculus and also some number theory next year. So it was actually kind of a very productive year, 2016. And I would have probably spent just a couple of months cleaning that out and or fighting with referees. So what happens in the case d equal to 1? It's related with the Mandelbrot set. There's a parameter where the logistic case when you have just an integrable case when the Julia set is an interval which has a equilibrium measure, nice equilibrium measure, which you also know from Schrödinger operators, from discrete Schrödinger operators. It's the free Schrödinger operator, Mathieu operator with lambda equal to 0, where everything is explicitly known, and so you have the density of states, which is the arc-sine distribution, which is very, very natural in statistical mechanics. So here, Julia sets and dynamical systems. It's also it's a distribution which is kind of nice. It has this kind of strange behavior at the boundary kind of, and it's also related to potential theory. If you charge an interval in the complex plane and you let just things go into equilibrium, then electrons will be at the boundary mostly. Density will be highest there, and so but you can compute the potential at every point. There's a subharmonic function which is here 0 exactly on the spectrum. It's a Lyapunov exponent in Schrödinger operator theory, and otherwise it's positive away from the spectrum. So that's very, very well understood. Everything is actually pretty explicit. The way how I prove this is using the potential theoretical picture. So what you have is, even if you have point measures, you can write down, and for what you call the density of states, kind of normalized density of states, which is the law of the random variable in the classical probability theory, and then the integrated density of states is the cumulative distribution function. If you write it like that, that's actually the way, that's this tree forest ratio, which is a difference between two potential values. There was one value where the potential, you take the potential away from the support of the spectrum, and the other one just at the boundary of the spectrum. So that's the thing. It's actually interesting in the case dimension 1, because you get interesting integrals, which I think we cannot, if you give that to a student, they cannot do it, and I also cannot do it, because it involves all kind of polylog stuff to do that. But you can compute that, and with the computer algebra system, you get you get actually the value here is at -1 is 2 times the logarithm of the golden ratio, which is just that thing, and then at the boundary it is 0, and that the fact that it's at the boundary 0 is related that the number of rooted trees grows polynomial, like n squared. On a circle, actually on a degree d graph, it also grows polynomial, but it depends on the degree. But anyway, the trees grow polynomially. It's the forests which grow exponentially, and so that's actually related to the forest, that's related to the trees, that's always bigger than that, just so if it's finite, and in this case we have a finite interval, so that's a subharmonic function. Just from the general theory of potential theory in the complex plane. So that's pretty cool, and so we have also seen last time there's a relation with the zeta function. You can express this as sum of zeta function values, which makes it even more interesting. So what happens in higher dimensions is kind of then, and then in order to prove, if you assume this to exist, this density to exist, you just have to only prove that the potential values exist. Now there is a little difficulty in the case of higher dimensions, 2 and higher dimensions, in that the interval is no more finite. The support of the spectrum of this density of states is no more finite. And that's very clear, because if you do barycentric refinements of a triangle already, the number of vertices, at the vertex degree explodes. And there's a relation between the vertex degree and the maximal spectrum value, which is actually given by a theorem in linear algebra, which I'm very fond of because it's so simple. It's called the lemma of Schur and Horn. I always call it Schur's theorem, but it's actually, if you look it up, it's Schur did so many things, and so it's actually better to call it Schur-Horn theorem, because Horn also worked on it, and so that you can distinguish it. So what is really needed in order to prove that these potential values exist is you need to show a decay here. This doesn't matter so much here. This is not a problem, because the potential value at here is, if this is finite, and this is boxed in between 0 and that finite value, and so that is no problem to exist. This cannot be problematic here. So the only thing you really have to show is that this interval produces a potential which is finite, which is not obvious. There are probability measures on a half interval. You can write down probability measures on a half interval, probability measures such that the potential is infinite. So just because it doesn't decay fast enough. But it's actually not so difficult to prove. What one has to do is you use this Schur-Horn lemma and you estimate. What happens in the higher dimensional case is that actually the eigenvalues will here kind of grow very fast, but the number of eigenvalues here are there are less and less eigenvalues where this happens, and this is related with the fact that in the barycentric refinement their vertex degree explodes for very few points, but then there's a stratification on how this grows, which you can explicitly give because you know what happens on the barycentric refinement with the number of vertices, number of complete subgraphs of any dimension. The F vector converges explicitly to a Perron-Frobenius distribution, which by the way is very interesting when the dimension goes to infinity. This is around, kind of maybe 0.7 something. It actually starts to accumulate here more. The dimension goes to infinity. This is kind of interesting, which I don't think has been looked at, but it's in the nature of this barycentric refinement operator. And so this has to be still to be written down precisely. But what happens is, if you look at the vertex degree distribution on vertices, what matters is the generation. So when you do barycentric refinement, there is one time when you have a vertex and you make a barycentric refinement, it still remains a vertex. So there is a kind of a generation thing. For example, here the triangle has here produced a vertex. So that's the first time it has been a vertex. This has been a vertex already before. This has not been a vertex also. This has been an edge before, but it became a vertex after barycentric refinement. In the next barycentric refinement, these vertices stay vertices, and all the vertices which you have stay vertices, but there are no new vertices which appear. And the new vertices have now of another generation. So what happens is you see the vertex degree here, it explodes every time. It's actually the barycentric refinement of the unit sphere. And that explodes exponentially depending on the dimension. This stratification can be explicitly given, it's exponential. So, and also this exponential decay here can explicitly give bounds how fast this decays. And as higher the dimension is, as faster it decays. So, but that's this tail distribution. And which is kind of still interesting. I mean, this whole density of states has not been studied at all in the but in higher dimensions we have no idea. We don't know about gaps, we don't know about Hausdorff dimension, we don't know about whether the logarithmic capacity exists. We don't know what is the potential value here. That's kind of the Lyapunov exponent problem, which I'm very fond of from the theory of Schrödinger operators. Like this, you can take, instead of 1, you take E, and then you can see what is the Lyapunov exponent on every point. You can ask, for example, is it true that on the density of states the Lyapunov exponent is 0 and everywhere else it's not 0? I actually think that in general that this Lyapunov exponent is positive. This spectral theory which could be relevance here. So I think that's it for now.